Hello there, Mr. Sutton here, bringing you the AB Calculus 3-3 homework solutions on differentiability part 2. For this problem, we're given this function with an absolute value in it, and we want the value of the derivative of f prime at x equals 3. Well, we know what absolute value means. We're going to have to turn this into a piecewise function to really evaluate it, especially because this 3 would zero out the absolute value, so this would be at the border value of our piecewise function. So piecewise function time. We're going to split this into two rules. We're going to have one rule for outputs that make the stuff inside here negative. So that would be if x is less than 3, the border value 3. If x is a number less than 3, then we want to force things to come out positive. So we're going to rewrite this as 2, and then we'll do plus negative x plus 3. So basically negate everything inside so that the output is forced to assume the opposite sign. And now we also have a rule for x greater than or equal to 3. We can put the equals on this second one. And if that's the case, if I'm plugging in numbers that are 3 or larger, absolute value doesn't need to do any work, and it might as well just not be there. So we can write this as 2 plus just normal parentheses x minus 3. Let's go ahead and just simplify this a little bit to make our lives easier. So I can write this first one as negative x plus 5, and then this one down here we can call this x minus 1. All right, or 5 minus x, that also works. Either way, let's go ahead now and figure out what the derivative should be at x equals 3. Now, before we can actually do that, we need to make sure that this function is differentiable at x equals 3. 3 is the border value, and lots of things can happen at border values. We might have a discontinuity. We might have a point of non-differentiability. We don't know until we test it out. So just taking f prime of the second rule here and plugging in 3 may not be enough on this problem. So let's go ahead and check the left and the right side limit for continuity. So now for the left side limit at 3, we're going to be using this less than 3 rule, so 5 minus 3, which is going to give us 2. For the right side limit at 3, we're using the greater than 3 rule, so that's going to be 3 minus 1, which gives us 2 also. And f of 3, because we always have to throw the function value in there when we're talking continuity, f of 3 just uses this second rule, so it just comes out to the same value as the right side limit, 2 namely. Okay, so we have a limit that exists and a function value that exists, and the limit equals the function value at x equals 3. So therefore our function's continuous at x equals 3, which isn't the whole picture, but it at least helps. So now we get to test the derivatives of each individual rule and see if the limits of the slopes are going to match up at x equals 3. So now we're going to take the limit as x approaches 3 from the left of f prime. And for that, we're going to take the derivative of this first rule and plug 3 into it. So the derivative of 5 minus x is just negative 1. It's a constant value of negative 1. So we actually don't really need to plug 3 into that. It's going to be negative 1 no matter what. Now we're going to take the derivative from the right side as x approaches 3. So we're going to take the derivative of this second rule, and that's just going to be 1. And we see here that the left side derivative and the right side derivative do not match. So therefore, this function is not differentiable at x equals 3, which means that trying to take f prime of 3 is not going to work out. There is no derivative there. It is non-existent. Choice E. On this problem, we're given this piecewise function, and we want to know if at this border value of x equals 3, our limit exists, our function's continuous, and or it's differentiable. So we're going to test for all of these kind of in one shot. In testing for differentiability, we have to test these first two anyway. So I'm going to start by getting my left and my right side limit at 3. Left side limit, I'm just going to plug into this lower rule here where x is less than 3. So that's going to be 3 plus 2, which is 5. For the right side limit, we're using the second rule. So 4 times 3 is 12, minus 7 is also 5. And then since we're talking about continuity, I mean our limit definitely exists. It's the same from the left and the right. But for continuity, we also need f of 3 to match the limit. So f of 3, that's going to use this first rule because we have the equals on the 3 here. And that also happens to be 5. Since our left side limit, right side limit, and function value all match up, since the two-sided limit matches the function value, we can say that we are continuous at x equals 3. So we know for sure options 1 and 2 are true. Now we test the rest of the tests we have to do for differentiability, which is basically seeing if the limits of the slopes match up at 3. So let me take the left side limit of f prime for this function. That's going to be the derivative of this top rule here, which is just 1. And now the right side limit of f prime, that's the derivative of my bottom rule here, which gives me a value of 4. Since the left and the right side limits of f prime do not match up, that means we are not differentiable at x equals 3, which means options 1 and 2 are true, but 3 is not. So that would be choice D. On this problem, we're given this function up here, and we want to know which of these statements is true. So we're talking about the function having a limit, being continuous, being differentiable at 2. Some of these can actually be eliminated right away. For example, if a function is continuous, then it will also have a limit at x equals 2. So this idea that we could have 2 only can be thrown out. And we can't be differentiable only, because if it's differentiable, it would be continuous and, again, therefore have a limit. So if you pick option 3, you've got to pick 1 and 2 as well. So let's get to the bottom of all this. To figure out what's going on, we need to figure out the limit as x approaches 2. And it's going to be a two-sided limit right away. To find the limit as x approaches 2 here, we're basically saying as I approach this function at 2 from the left and the right. Now, how do I approach from the left and the right? Most piecewise functions, we would have an expression for if x is less than 2 and if x is greater than 2. But here we have x not equal to 2 and x equal to 2. This not equal to 2 basically means if x is less than 2 or x is greater than 2. It stands for both of those rules. So to get the two-sided limit, I just have to take the limit of this top rule here. So limit as x approaches 2 of f of x is going to be the limit of this stuff. And I'm actually going to go ahead and factor it because I know if I just plug in 2 outright, I'm going to get 0 over 0. So factoring the numerator, I have x plus 2 and x minus 2 up there. X minus 2's cancel, leaving me with the limit of x plus 2 as x approaches 2. And just plugging that in now, we have 4 for that. Now we also see that f of 1 is going to be 2. So we definitely have a limit that exists. It's 4. So option 1 is true. Option 2, though, not so much, because f of 2 equaling 1, that means that the limit and the function value do not match up. So this function is not therefore continuous. So we can eliminate option 2. Since we're not continuous, that implies that we also are not differentiable at x equals 2. So in the end, only option 1 is true. So choice A. For this problem, we want to know which of the following functions shows that the statement, if a function is continuous at x equals 0, then it is differentiable at x equals 0, is false. So we have 5 different functions here, and we're basically trying to figure out one that is continuous but not differentiable at x equals 0. So the quick way to do this is if you know what these look like. Continuous but not differentiable, there's really only 2 ways you end up with that. That is if you have a pointy part of the graph, like a cusp or a corner. The other way you could get that is if you have a vertical tangent. Now, looking at these different functions here, f of x equals x to the 1/3, if you remember what the cube root function looks like, you do realize that it has a vertical tangent as you go through the origin. So you could very quickly pick choice C and be done with this. If that didn't occur to you, that's okay. We can go through and test each of these for both continuity and if they pass continuity, the slope limits matching up. So starting over here at choice A, testing for continuity, I'm going to rewrite this without the negative exponent to make my next explanation more clear here. So this is really 1 over x to the 4/3, or 1 over the cube root of x to the 4th. Now, this clearly has a discontinuity at x equals 0, because that would zero out your denominator. So because we have a discontinuity there, this would not show the statement about continuous but not differentiable to be true, because it's not even continuous. So this is a no. Moving on to answer choice B, which is 1 over the cube root of x. This has the same issue as A, 0 in the denominator. So also discontinuous, so that won't help us out. Looking at choice C, this is the cube root function, which is known to be continuous. There's no breaks or holes in it. So now that means we have to test out the slope of the limit of the slopes. Now, the way we're going to do this, since it's kind of hard to do left versus right limit without a piecewise function, we're basically going to see if the derivative itself is continuous. You don't need a continuous derivative to prove differentiability. That actually is more than you need, because you don't need the function value to equal the limit of the derivative. You just need the limit of the derivative to exist. However, continuity gives us more than what we need. So if we have continuity, we know that our function is differentiable. Continuity of the derivative means our function is differentiable. So derivative of this is going to be 1/3 x to the negative 2/3. And that is a function that, if you imagine this x being in the denominator because of the negative exponent, this is not going to be continuous. We're going to have a discontinuity at x equals 0. So that is not enough by itself necessarily to prove that we don't have differentiability, because again, the derivative does not have to be continuous. It just has to have a limit that exists. So this is a maybe. This indicates that perhaps we're not differentiable at x equals 0. So let's check out the other two answer choices, and if we can't eliminate them, then we'll come back to this one and analyze it a little bit more deeply. All right, so answer choice D, this one, if I write it in this form, this is essentially a cube root function with the fourth power plugged into it. That's not going to make anything undefined, so this is one that's going to be known to be continuous. Checking out the derivative of this thing, 4/3 x to the 1/3, that's also kind of a cube root function, and that means the derivative is also continuous. If the derivative is continuous, then we're guaranteed that the original function is differentiable. All right, so this is a no then, because we needed a function that was continuous but not differentiable. So moving on to choice E, this is a polynomial which is known to be continuous. Derivative of that, 3x squared, is also a polynomial known to be continuous. So that means the original function is differentiable, which means this is also not a good one for proving continuous but not differentiable. So that means answer choice C then, by process of elimination, is the only one we can pick. On this problem, we want to know if this piecewise function is differentiable at x equals 1. So to do that, we need to check out continuity and then the limits of the slopes. So for continuity, let's check our limits from the left and the right first. Left side limit as x approaches negative 1, that'll be 3 times 1 squared, which is 3. Right side limit as x approaches 1 from the right, that'll be 6 times 1 minus 3, which is also 3. And then since we have to prove differentiability, we have to prove continuity rigorously here. So we also need to look at f of 1, which is just this first rule. That's going to be, again, 3, from 3 times 1 squared. So because our two-sided limit matches our function value at 1, that means that we're continuous at x equals 1. So we can take our next step and check the limits of the slopes. So let me check the left side limit of f prime in this function. That would be the derivative of this first rule, which is 6x, and we're still evaluating that as x approaches 1. 6 times 1 would give us 6 for that limit. And then the right side limit of f prime as x approaches 1, that would be just the derivative of this bottom rule, which is also 6. So because my left and right side limits of my f prime match up, that means that this function is differentiable at x equals 1. On this problem, I'm given this function up here with an a and a b in it, and we want to know the values of a and b for which this function is differentiable at x equals 1. So we're basically going to pretend we're proving differentiability at 1, and that's going to give us some equations that we can use to solve for a and b. So let's do continuity first. That's the first part of a differentiability proof. So we're going to show that the left and right side limits and the function value all match up. So left side limit as x approaches 1 from the left here, that's going to be this first rule, so that would be 1 plus b. We don't know what b is, we'll just have to leave it that way. Right side limit, we're going to use the second rule now, plugging 1 into that. So that would be a times 1 squared, which is just a. And now, since we're showing differentiability and continuity, we need to include the function value, f of 1, which is the same as the left side limit, 1 plus b. So since all three of these things have to match up, these things, at their very least, have to match up for the limit to exist. That means that 1 plus b must equal a. Not enough to solve for a or b yet, but we're going to get another equation that will hopefully help us turn this into something useful. So next, I'm going to check out the limits of f prime. My slope limits have to match up if I want differentiability. So limit as we approach from the left at 1 of f prime is going to be the derivative of this first rule. That's just going to be 1 plus, well, actually, b is a constant, so that's going away. So that's just going to be 1 for that derivative. And now right side limit of f prime, that's going to be 2a x to the first, so 2ax. Since my slope limits have to match up, that means that 1 equals 2ax. And actually, let me finish evaluating this limit, because I haven't actually plugged in 1 yet. I just took the derivative. I didn't actually plug in 1. So that's going to be 2a. All right, so that means 1 must equal 2a, which means that a must have a value of 1/2. Well, now we can actually plug a back in up here to have 1 plus b equals 1/2. And if I subtract 1 to get b by itself, I end up with a b value of negative 1/2. So we've got a equals 1/2, b equals negative 1/2. That's going to be answer choice A. For this problem, we have a function with some properties given by this table here. So at -1, 0, and 1, they've given us the left side limit, the right side limit, and the function value. So let's see what we can say about continuity and differentiability at these different values. So let's go through and just eliminate what we can. Choice A, f is continuous at x equals -1. Well, all three of these things have to match up for us to have continuity. The limits have to match up so the limit exists, and the limit has to actually match the value of the function value. We see here for -1, the limits don't even match up, so that means our limit does not exist, and we are not continuous at x equals -1, so this is a big no for option A. Choice B, f is continuous at 0. Well, here the limit exists, it's -3, but the limit at 0 does not equal f of 0, which was 5 instead. So because those don't match up, we're not continuous at x equals 0 either, so that's another no. On to the next one, continuous at 1. Well, here we have a limit that exists, and it matches the function value. So since our limit as x approaches 1 and our f of 1 match up, we can say we're continuous at x equals 1. So that's going to be what we're going to end up picking. But let's just take a look at choices D and E just for the sake of argument. So these are talking about differentiability at 0 and 1. So differentiability at 0 you can actually disprove because we're not continuous at 0, so we're not going to be differentiable. Differentiability at 1 you can't really disprove, but we don't have enough information to prove it. We would need to know the f prime limits in order to test this part of the differentiability test. So this is going to be another no just based off of lack of information for choice E and just being outright wrong for choice D. So then choice C is our answer. On this problem, we're given this piecewise function with these mystery constants, C and D. They're telling us that f is differentiable at x equals 2, so we want the value of C plus D. So the way we're going to do this, we need to figure out what C and D are and then add them together. To do that, we're basically going to pretend we're proving this thing is differentiable using our different tests. So we'll start with the test for continuity, then we'll check out the test for slope limits. So for continuity, we first consider the left side limit as x approaches 2 from the left. That's going to require us to plug 2 into this first rule here. So that's going to be 2c plus d. Next, the right side limit as x approaches 2. Plugging 2 into the second rule now, that's 4 minus 2c. And because we're talking about continuity at this point, we also have to include f of 2, which is just going to have the same value as this first rule here, 2c plus d, because 2 is included in this interval. So because these three things have to match up, that means we can say that 2c plus d equals 4 minus 2c. Not much else we can do with that equation at this point. I mean, we could combine the c's, but that's about it. So let's go ahead and move on to the next part of this, which is testing the slope limits. So left side limit as x approaches 2 of f prime. Now I'm taking the derivative of this first rule up here. So that's going to be, let's see, c, because we have a cx, that's a linear function there. and then this d gets differentiated away to 0. So it's just c then for that derivative as x approaches 2 from the left. As x approaches 2 from the right side, now we're taking the derivative of this bottom rule. That's going to be 2x minus c, but we still haven't actually plugged 2 into it yet. This is just the derivative. Plugging 2 into this expression now, we have 4 minus c. And we know that since these slope limits have to match for differentiability to occur, that means that c must equal 4 minus c. Well, that there's an equation we can actually solve. Adding c to the other side for 2c, and then dividing, we end up with c equals 2. Now that I know the value of c, I can go back and solve for d in this first equation I wrote. So I'm going to rewrite this as 2 times 2 plus d equals 4 minus 2 times 2. So moving things around a bit here, we've got 4 plus d and 4 minus 4, which is just 0. So then that means d must equal negative 4. And that answer choice, well, we're not ready to pick an answer choice yet. There's an answer choice for negative 4 right here. There's also an answer choice for that c value of 2. However, you have to read carefully. They wanted the value of c plus d. So that means we need to do 2 plus negative 4, which is going to give us negative 2, which is choice B. On this problem, we have a function that's continuous at x equals 3. We want to know which of these must be true. So going through these, choice A, they're saying that f of 3 is less than the limit as x approaches 3. Well, this can't be true if we're continuous, because continuity means that the limit and the function value should be exactly equal to each other at that point. So since the function value and limit have to equal each other, this is a no for choice A. Choice B, they're saying the left and right side limits don't match up. Well, continuity means the limit exists, which means the left and the right match. So this is also a no. The limit should exist. Choice C, they're saying that function value and left and right side limits match up. And this is one way of proving continuity. Since the limits equal each other, the limit exists. And since the limit, which exists, equals the function value exists, limit equals the function value, all the conditions of continuity have been met, most particularly limits and function values agreeing. So this is the one we're probably going to end up picking, but let's just take a look at the other two. D, the derivative of f at x equals 3 exists. Well, we're not guaranteed that because we haven't actually tested the limits of f prime yet. So we could have a cusp. This is kind of a counterexample where you could be continuous but the derivative doesn't exist, like at a cusp, or a vertical tangent would be another way for this to be false. And then the last one, derivative of f is positive for x less than 3 and negative for x greater than 3. Well, how does continuity have anything to do with the derivative of the function? I mean, we could have a horizontal line, that's continuous, but the derivative is going to be neither positive nor negative anywhere. It would be exactly 0. So if you consider the case of y equals 1 or any other horizontal line, that's more than enough to blow this answer choice out of the water. So then choice C is the only one that makes sense.